Now, the only difference with this simulation, I pointed out before we look at it, is that, remember, with the 4 vehicles and loader simulation, we actually had the loaders down the left-hand side and the next events across the top. This is just the other way around, with the next events down the side and the 10. We're going to be simulating 10 people walking into the shop. Okay, so first 10 people who walk in the shop. The only difference is the 10 people are across the top. The next events are down the side of the simulation. So, but it says, I mean, it doesn't matter which way around you do them. It says, as long as you've got a list of all the next events and a list of all the event and things that are happening. So the first thing is we want the inter-arrival times. When do people arrive in the system? So we generate a random number, 0.471, and that will give us an inter-arrival time. Well, if we start the clock at time 0, and we find that the inter-arrival time is 38 seconds, then somebody arrives into the shop 38 seconds after it opens. Okay? And they go into the system, because that's when they arrive, and they go into the system is the shop. Now, I did an example whereby I had a random number of 0.539, and that gave us a travel time of 46. I've rounded these off to the nearest whole second, but it was 46.4 seconds, but 46 seconds up there. So that was the example that we did.
The inter-arrival time is between 0 and what?
Sorry?
The inter-arrival time, is that between 0 and what?
But the inter-arrival time is the time between one arrivals and the next, and that can be any number of seconds. It's just we're simulating that. The simulation is giving us the inter-arrival times. Okay? I did an example of a random number of 0.539 and an inter-arrival time of 46. That's just one of those 10. Okay, just to illustrate where that one came from. But the others have all used whatever. So, for example, what we're saying is that the clock starts at time 0. 38. We simulate an inter-arrival time. 38 seconds later, somebody walks in the shop. A random number of 0.051, an inter-arrival time of 3. In other words, 3 seconds after the first person, the second person arrives in the shop. So after 41 seconds, there's another person in the shop. Then another inter-arrival time, 41 seconds after that. Somebody else comes in, and then 20 seconds after that, somebody else comes in. So we're simulating when every person comes in to the shop in terms of their position relative to the one before, inter-arrival time. So, if we now go down into the next event, so the first person arrives into the shop, and they go into the service, because there's nobody there, the shop's just open. You've always got a startup effect with a simulation, where nothing's happening to start with, nobody in the shop, so they could go straight into being served. Okay? So they go into the system for service at time 38. Then we generate a random number for the service time. This is all with lander is 1, obviously, average inter-arrival time of 1 per minute, which was given. And service time of 1.5, so 1.5. So we got into we random number for the service time, and that gives you the length of the service. I think I chose, just to be consistent, 0.7. Random number was 0.746. It's that one there. So, I mean, I simulated as an example that one there, but that's just one of the ones in the that was the service one that we did, 55 seconds of service. But all these random numbers give you different service times. So it's a matter of next event. So if somebody goes into the service at time 38, they take 136 seconds to be served and processed. They will leave at 136 plus 38, which is 174. And the person who arrived didn't queue at all, because they walked in the shop, there was nobody there, they went straight into being served. The person who was serving, technically, I mean, you could put that in brackets if you wanted, but waited 38 seconds doing nothing until somebody arrived in the system. Okay? And we're just recording information here. So time in the system, how long were time in the system is from when they arrived to when they left, including queuing or being served and whatever. In this case, it didn't queue, but so they were in the system for 136 seconds. Then we go to the next person. They arrived into the system at time 41 seconds, 3 seconds after the one before. They can't be served until the one before has just finished at time 174. So they go into service, because it's one at a time service and they've got to follow on, and that's what simple queue means, one at a time service. So they would go into service at time 174. There would be a random number, there would be a service time, 17 seconds in this case. They would therefore finish at 191. They waited for 133 seconds from when they arrived to when they went into the service, whereas the server now went directly from doing person 1 to person 2, so they didn't queue at all. And you just carry on with your next events building up. When people arrive, obviously somebody can't be served until all the people in front of them have left the system and been served. And we just keep a record of how long people queued, how long the server waited, how long people were in the system. And here, as I say, all we've done is simulate 10 people into the system.
So in the exam, these random numbers, will we get a range of like inter-arrival times? So to put them.
Well, there's two things about random numbers in the exam. First of all, you will be given the random numbers in the exam because if you all had your own, if you use your calculators or whatever, every answer will be different from everybody in the class, and there's no one answer. And obviously, some people might get a nonsense, well, not nonsense, but I mean, no queuing, and other people get queuing, and it wouldn't, it would. Although you can say, well, that's fair because it's a simulation, but I want an answer. I can see everybody's done the same thing. So you'd be given the random numbers in the exam. But I mean, I think the real point you're making is something I'm going to answer in a minute. So if you just hold it a second, I'll come to it. But what we've got now is so we can simulate 10 people. Now let's just see what have we got out of this simulation, because we're interested in knowing things about how long people wait in the system and so on. And what information can we get? So we might be interested in average queuing time. What is the average time that somebody queues in this shop? How long do they queue? Well, we've got the queuing times here of every one of these people who arrived in the shop. So if we added all of these up and then divided by 10, because there's 10 people, you would get the average queuing time of people who walked into this shop. Now, if you do that, you'll find that 0 plus 0 plus 65, 128, 119 plus blah, 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 comes to 725. I mean, you can check it out if you want. And the average queuing time will be 72.5 seconds. So the sum of that row plus divided by 10 the number of people, 72.5 seconds. Now, we can, because we have the theory, because we know we're simulating a simple queue, we know what the answer is. I mean, we've got a formula from our theory which tells us what the average queue time is, and therefore we can go to our theory, and we know the formula, lambda over mu, mu minus lambda. If lambda is 1 per minute, mu is 1.5 per minute, we get, working through, we get 1 over 0.75 or 4 over third minutes, or 1 1/3 minutes, or 80 seconds if we wanted in seconds. So in other words, our theory gives us 80 seconds. Our simulation of only 10 gives us 72.5. In other words, we're not far off even just simulating those 10 people into the system. And if we simulated the first 100 people in the system, we'd get an answer. We wouldn't get exactly that 80, but we would get pretty close to that. And if we did a very long simulation of 1,000 people coming into the shop, you would eventually get an answer where the average queuing time would be about 80 seconds from your simulation. Because we modelled something that we know the results for.